we have already seen the definition of these four basic signals. Now, try to understand their importance in practical analysis. Try to imagine a space shuttle which has a huge mass of fuel, and while in flight, the mass keeps on decreasing as the space shuttle moves away from the surface of the Earth. The calculations required to determine the ideal fuel amount are not that easy, and it will not be nice for a student to directly think and analyze real life cases. Just for the introductory knowledge for the students, these signals are used. Consider lightning. A single lightning strike can create a potential difference of 1,000,000 volts, which result in huge loss of resources and finances every year. That's why we use earthing systems and such protection devices. Impulse signals help us to predict what could happen to our devices in the worst case. Simply said, impulse signals are used in stability analysis of systems. But we will be focusing more on other three signals, as our focus will be on time domain analysis and related parameters. These three signals are the simplest types of signals which can be used as inputs for a common control system. These signals are also referred as sudden type input, velocity type input, and acceleration type input. You might be thinking how these signals got the other names. For example, consider ramp signals. These are called velocity type inputs because they mathematically represent constant velocity motion in control systems analysis. Ramp input increases linearly with time, mimicking the position output of a system moving at constant speed. These signals got their name from the graph, as they represent the graph of constant position, constant velocity, and constant acceleration, assuming initial velocity to be 0. If you consider these graphs of mechanics, you will find these graphs looks exactly similar to the definition of the above signals, and that is the reason why step signal, ramp signal, and parabolic signal are referred as sudden type input, velocity type input, and acceleration type input. The time response of a control system means how the response behaves in accordance with time when a specified input test signal is applied to a system. The response when we talked in the first unit was divided into two components, zero state response and zero input response. But here you have to drop that completely, as we will be dividing the time response into two components, the transient response and steady state response. Theoretically, steady state means a state of the output of a control system as the time approaches to infinity. But obviously, it is not possible. How long can you wait for the steady state to achieve? No one is immortal. That's why the transient response is defined in terms of time constant. Generally, the time taken is equal to 4 times the time constant, and the response up to the 4 times of time constant is considered the transient response, and after that the response is referred as steady state response. The transient part of time response reveals the nature of response, whether the system is oscillatory in nature or what is the damping factor of the response, and also gives an indication about its speed. The steady state part of the time response reveals the accuracy or steady state error of a control system. Transient response of the system depends on the order of the system, whereas the steady state response depends on the type of the control system. This point will be verified in the later lectures. For now, you just simply write it down.